So the member OA rotates about the horizontal axis through O with a constant counterclockwise angular velocity of 3 radians per second. As it passes the position theta is equal to 0 degrees, a small block of mass m is placed on it at a radial distance of 450 millimeters. If the block is observed to slip at theta is 50 degrees, determine the coefficient of static friction between the block and the member. So the first decision we need to make here is the coordinate system that we want to use. And I would argue that since we have a rotating system, the most appropriate one would be the r theta coordinate system. So for this one, we want to set it up so that our origin is at the point that we're rotating about, and the r direction is going to be in the direction of the member that's rotating, and theta is going to be 90 degrees to it, and it's going to measure the change in this angle. Okay. So, next thing I want to talk about is our point of interest. So, we're interested in what happens at this theta is equal to 50 degree position. Reason is we start to get some slippage of this block along the ramp. So, I'm going to write in here, theta is equal to 50 degrees, and we're measuring it this way. And we also know the angular velocity at this instant in time. We're told that it's the whole time going to be rotating at this constant counterclockwise angular velocity of 3 radians per second. So that's going to be in this direction. Alright, I'm going to call it, theta dot. And it's going to be 3 radians per second. Okay, so this is the angular velocity of our member. We also know the angular acceleration. Because we know that it's a constant velocity, it's going to be a 0 acceleration. So we can mark this in as theta double dot has to be equal to 0. Alright, so we've got all these things sorted out for the theta dot, theta double dot. What we want to do now is probably sort out what's happening in terms of the radius, okay? Because these are going to be the components that go into our velocity and acceleration equations for the r theta coordinate system. So, if we look at r, it's going to be the distance from our origin over to our point of interest, and we're measuring it this way as the positive direction. We're told that at our point of interest it's 450 millimeters. So now we just need to sort out what r dot and r double dot are. So r dot is going to be the velocity of our block in this direction, up and down the ramp. Okay, so at our point of interest, when theta is equal to 50 degrees, we're told that it's just the moment when it's about to slip down the ramp. So it hasn't quite started to move yet, which means that it's going to have a velocity of 0. Okay, it's about to move, but it hasn't quite yet at that instant. Similarly, for this r double dot, it's the acceleration in the direction of the ramp, and again, if it's the position that we're considering is like imminent movement, it hasn't quite happened yet, so the acceleration at that point is 0. It's about to have one, but not quite yet. So that sorts out all of these different parameters that are going to go into our acceleration equation in a second. So let's just quickly write it out. So in the r theta coordinate system, obviously we have components in both of those directions. Okay, so AR is the radial component, and A theta is the theta component. And if we write it out in the longer form, it looks like this. Okay, so in a second, when we sum our forces, it's going to be equal to the mass times acceleration, and we're going to do it in the r direction, which we could use this equation for, and the theta direction, which we can use this equation for the acceleration. So before we get to that, we need to draw a free body diagram. So if I just scroll down a bit, we're going to draw the free body diagram of the block, and I'm going to do it in our position of interest, which is when theta is equal to 50 degrees. So it's at some angle here. So we're told that this is rotating, like this is the vertical plane that we're looking at here. So it's going to have gravity involved in the situation. So if we apply it as a weight of the block, it's going to be acting directly down. And we also know that this block is sitting on a surface. So we're going to have a normal force applied perpendicular to the surface. So it's going to be back up like that, making a 90-degree angle in here. So you can work out the angle. It's always going to be in here. The angle between the normal and the weight vectors is always going to be the same as the angle of the inclined plane. And if you want to, you can prove it. You can just kind of make a triangle in here. Okay, this is a right angle. All of the different angles in here have to add up to 180 since it's a triangle. So 50 plus 40 plus 90 degrees gives you that right angle. Alright, so if you want the angle that's made in here, okay, we can do that as well. We know it's going to be a right angle since it's perpendicular, so 40 plus 50 in here gives you a right angle. So this angle corresponds to this one on our free body diagram. Alright, so we have one more force that we need to apply, and this is the friction force, which is the one we're probably most interested in because it's going to help us solve for the coefficient of friction. So I'm going to assume that as this rotates around, at our instant, this block is going to try and fall down the ramp. So friction needs to oppose the direction of motion, which means it's going to be directed back up the ramp. So the force of friction is equal to the coefficient multiplied by the normal force, and we're looking at the static situation where movement hasn't quite occurred. So it's going to be this static friction coefficient that goes in there. So if I draw our directions as a reminder, this is r and this is theta. So now what we're going to do is apply our sum of forces equation in both of our directions. We know that the acceleration in both directions, we can use these equations, and we should be able to solve for the unknown, which is us. So I'm going to start with the theta direction. So that's what we've got. So the sum of forces in the theta direction comes off the diagram. So that's perpendicular to the ramp. So we're going to have n going up, and we're going to have a component of this coming back down. So it's going to be minus mg. It's going to be the cos component. So cos 50. Yep. And on the right hand side, we know it's equal to the mass times acceleration. So technically we could use this form of the acceleration. However, we've got a bit of a trick with this question in that we're told that this thing is going to slide down the ramp. So technically, the only acceleration that can occur is going to be in this direction, so it's restricted. That means that there's going to be no acceleration perpendicular to the ramp. So instead of using this equation, we know that it's going to be equal to 0, okay? No movement perpendicular to the ramp, so the mass times acceleration here has to be equal to 0. Okay, if it was unrestricted and we could have motion up and down perpendicular to the ramp, then of course we'd use this one in here. So if we rearrange for n, we're going to get it equal to mg cos 50. Alright, and we're going to be able to use this in a second to put into our friction equation. So if we now sum forces in the other direction, we've got that. So the left-hand side comes off our free body diagram. So again, r direction is parallel to the ramp. So we're going to have this in the positive r direction, so it's mu s times n. This is completely in the theta direction, so it's not going to contribute. And this one here, it's going to be going backwards, so it's going to be minus mg, and it's the sine component that we need to consider. So on the right hand side this time we are going to have some acceleration in that we know it's going to be going potentially down the ramp. So we can substitute in our equation which is this part here, alright, from our expression for acceleration in the r theta direction or r direction. So it's going to be r double dot minus r theta dot squared, and we've already taken care of the signs of this in our things that we're going to substitute in. So that's why I've just substituted it in as positive, because it's a general form from the equation. Alright, so the next step is we're going to need to try and solve this for the coefficient of friction. We can substitute in our normal force into this equation, and what we're going to find is that all the mass terms then cancel and the solution is independent of whatever the mass of the block actually is. So let's substitute it in. Okay, so that's what we get, and you can see we have mass in every single term, so each of those is going to cancel out if we divide through by m. Now we're going to need to rearrange this for mu s on its own, so let's go ahead and do the first step of that. So on the left hand side I'm just going to leave the term with mu s in it and move everything else to the right hand side. And that's what I get. And now to solve for mu s, we just need to divide by g cos 50. Alright, and we're up to the point where we can substitute in. So we know r double dot, r and theta dot because we wrote them out just before. Alright, so up here we had each of these values here as well. So we can go ahead and just substitute straight in. So theta double dot we said was 0. R we said was 450 millimeters, or if we convert these to like the base units, I'm going to put it in as 0.45, that's in meters. Theta dot was already in base units, it's 3 radians per second, it gets squared. G is 9.8, and it needs to go on the bottom line as well. Oops, sorry, cos. So if you type all of this into a calculator, you end up with 0.54. So that's the answer for the static friction coefficient in order to maintain the rotation of the block without moving up to 50 degrees. Okay, so that's the answer to this question, and I'll see you in another video.